Hello. Today we're going to be discussing something known as the central limit theorem in statistics. It allows us to calculate the mean and the standard deviation for a sample of items instead of an individual item. To kind of lead into it, consider the following situation. This is kind of extending off of a penny investigation that we completed in class. Which situation would you find more peculiar and why? Situation A, you find a single penny and its year is 1972. You take a sample of 20 pennies and their average year is 1972. If you think about it, it would probably be far more peculiar if situation B occurred. It's a lot more peculiar surprising because you're taking a sample of 20 pennies with an average of 1972. And that would be more interesting because that would mean that the majority of the pennies were quite old as compared to situation A where you're finding just one penny that is old. So this is really what the central limit theorem is getting at. The central limit theorem shows us that the standard deviation for the distribution of samples shrinks compared to a distribution of individual items. That is, you get a far less spread when you take a sample and average them than if you just find a few. So if your sample is larger, it's going to narrow in on the actual average value when you calculate the averages of all of those distributions. To extend on what we were doing in the penny investigation, we found the following. So the population distribution, that is like the pennies that were in the bag, looked something like this. What you'll see if you just look at this natural distribution, it looks like the average aged penny is between 1995 and 2000. These are all the pennies. So what we did is we drew a bunch of samples out, we calculated their average, and we did this over and over and over again. And then we plotted each of the averages in a distribution. And here's the distribution of the sample means. So each of these bags represents a drawing of a bunch of them, and then we averaged each of their ages and we plotted them. And what you'll see is our spread is a lot less than in the individual cases. The reason that our spread is less is because we're averaging all of these, and so they're going to narrow in on that mean. You'll see the mean is still the same average that we had before. The difference is there's far less spread. The reason there's far less spread is because we've taken a bunch of samples and averaged them, and when you take a bunch of samples and you find each of the individual samples average, and then you plot those, they're going to naturally narrow in on the true average. It's washing out the highs and the lows. That's what we found. If you look in a textbook, it will say the following. In the prior investigation regarding the year and age of pennies, we found the following conclusions. It's what's known as the central limit theorem. Part 1, if samples of size bigger than or equal to 30 are drawn from any population with an average of mu and a standard deviation of sigma, then the sampling distribution of those sample means will approximately be a normal distribution. The larger the sample size, the better the approximation. You'll notice first off that they have the exact same mean. They have this exact same average. So because of this, the distribution of sample means has a mean that will equal the population mean. So the average of the sample means is going to equal the mean of the population. Should make sense. They're going to average towards the average. The second thing they said is what we talked about with the distribution. The distribution is going to narrow in. As you increase the sample size n, the sampling distribution, standard deviation, or spread decreases. If this is my parent population that I'm drawing from, if I took samples of size 5 and then averaged each of those samples and plotted them, I get the following distribution. You'll see the spread is already narrowed even if we just sample size 5. Sample size 16, the spread is even smaller. Size 25, even smaller. 30, even smaller. So we see the standard deviation shrinks as I increase my sample size. And the formula in how it shrinks is given right here. We take our population standard deviation and we're going to be dividing by the square root of n. In order to derive this, you'd have to take a calculus statistics course. Hopefully, you can just fundamentally understand why. Because my samples distribution has to narrow in, I see that this is getting smaller because as n increases, it's a bigger number. If you have a bigger number in the denominator, it will make the entire item smaller. So that's the formula for it. In conclusion, any population distribution, if you take it's a bunch of samples and then you average each of those samples, you're going to approximately estimate with a normal distribution. If you start with a normal distribution, you're certainly going to get a normal distribution back. But the central limit theorem says if you even start with any population distribution, no matter how weird or skewed it is, you're going to get a normal distribution as long as your samples are of size 30. If you start with a normal, you can take samples of any size. So that is an important difference. If you have any population distribution, you don't know what it looks like, you need samples of at least 30. If you know that it's normal to start with, you can take samples of any size because it's already normal to start with. So let's consider the following situation. You can kind of see how it's used. So cellular phone bills for residents of a city have an average of $63 and a standard deviation of $11. Random samples of 100 cell phone bills are drawn from this population, and the average of each sample is determined. Find the mean and the standard error for the average of the sampling distribution. So we're going to be using the central limit theorem. Step 1, verify that we can apply the central limit theorem. And so if I look, it didn't say anything about the original population being normal. It doesn't necessarily look normal. It has maybe some symmetry to it. But because it's not normal, we need at least a sample of size 30, and we do since our sample is a size of 100. So we can apply the central limit theorem. Step 2 is now we're going to apply it. The average of the sampling distributions, average, is going to be the same as a population. And the population had a mean of 63. So my distribution of the sample means will have an average of 63 as well. The standard deviation will be the standard deviation of the population divided by the square root of n. In this case, that's going to be 11 divided by the square root of 100. The square root of 100 is 10, so 11 divided by 10 is 1.1. So my distribution for the sample means will have an average of 63, but it will be far more narrow because I am zooming in on the average. If I look at what the actual distribution is, it looks like this. Far more normal than the situation we had up above. So I see average is 63, and the standard deviation is $1.10 for the distribution of sample means. What this means is if I took a bunch of samples and I found the average of each of the samples, they would tend to be very close to $63, and their spread, their standard deviation, would be $1.10. So they shouldn't be that far away from $63 if I took a bunch of samples, size 100 in each sample, and found their average. Situation 2. The training heart rates of all 20-year-old athletes are normally distributed with an average of 135 beats per minute and a standard deviation of 18 beats per minute. If we take random samples of size 4 from the population and find each of those samples average and then plot them, we'll find the following distribution. Our goal is to find the mean and the standard error of the mean of the sampling distribution. So first, verify we can apply the central limit theorem. If you look, we don't have samples of size at least 30, and that's okay in this case because our population is normally distributed. And if we start with a normal distribution to start with, no matter what our sample sizes are, we're always going to have a normal distribution. So since this population is normally distributed, we don't require samples of size 30 or more in order to apply the central limit theorem. The average for the distribution of sample means is going to have the same average as the population, which they said was 135. The standard deviation needs to be the population standard deviation divided by the square root of our sample size n. Our population standard deviation was 18 beats per minute. We were taking samples of size 4, so the square root of 4 is 2. 18 divided by 2 is 9, which means if we took samples of size 4 for athletes, found their average, and plotted them, all of those samples averages would be very close to 135, and their standard deviation would be 9. So those averages would be very close to 135. The majority, 68%, would be somewhere between 126 all the way up to 144. The individual samples averages using standard deviation of 9. 9 above, 9 below. And the empirical rule. Going to give you a chance to try. So given the following population distribution, determine which option most closely resembles the sampling distributions of the means. Justify your choice. So you need to see up above this distribution, certainly not normal, doesn't need to be because we're assuming they take a large sample size. The average for this is 16.5. Standard deviation is 11.9. If you took and plotted the distribution of sample means, which distribution would you expect to find? So pause the video now, come back and see how you did. So the first thing is if we're going to take and draw a bunch of samples and calculate their averages and plot them, it's going to be the same average as the population. So we need an average of 16.5. And if I look, there's only two that do that, A and C. B has a sample of 1.65, so it can't be this one. Now I need to use the sample or the standard deviation. The standard deviation for the population is 11.9, If I draw a bunch of samples and average them, it will shrink in that standard deviation. So I need a standard deviation smaller than 11.9. This has the same one, so it can't be this one. It has to then be C. Same mean, much smaller standard deviation since we took a bunch of averages and plotted them. Finally, now we're going to be using the central limit theorem to be calculating some probabilities or z-scores for the distribution of sample means. Recall that the z-score is equal to our measured value minus the mean divided by our standard deviation. The only thing that changed is now is the standard deviation for our sample means is our population divided by the square root of our sample size. Otherwise, it's the exact same z-score calculation formula that we used before. Example of using it. So a legislator is considering adjusting the driving age, so a study on time behind the wheel is conducted. Drivers between the age of 15 and 19 spend on average 25 minutes behind the wheel daily. You randomly pick 50 drivers between that age range. What is the probability that the average time that that group spends driving each day is between 24.7 and 25.5 minutes? Assume that the population standard deviation is 1.5. So first off, verify that we can apply the central limit theorem. And we can, not because the population is normally distributed, but because our sample size is equal to 50, and 50 is greater than 30. So we need a sample size of at least 30, and we do. So now we can apply it. The average for our distribution will have the same average as the population, and that was assumed to be 25 minutes. The standard deviation for our sample we'll have a standard deviation of the standard deviation of the population divided by the square root of n. Standard deviation for the population is 1.5 minutes, and we drew a sample of size 50. So you're going to need to grab a calculator because the square root of 50 is not an integer value. And when you do that, you end up getting 0.212 for our standard deviation. Now we can convert to a z-score. We want to know what's the likelihood they're between 24.7 and 25.5. So I need to find both of those. So the z-score for 25.5 first. Let's do 24.7 because that'll be the left one. So 24.7 minus the average is 25 divided by, well, we found this right here already. The population divided by the square root of n, that's 0.212. So our first z-score is going to end up being negative 0.3 divided by 0.212. That's negative 1.415. Our next z-score would be the 25.5 minutes. So 25.5 minus the average of 25 divided by 0.212. Z-score for that would be 0.5 divided by 0.212. I get 2.358. Now I can use those z-scores to get the probability. My left bound is negative 1.415. My right bound is 2.358. And then I grab my calculator and I go to second distribution, normal CDF. My left bound is negative 1.415, right bound 2.358. My mean is 0, my standard deviation is 1 since I'm using z-scores. And I'm getting a probability of 0.912 or 91.2% likelihood that the average of that sample will be in between 24.7 and 25.5 minutes. That's a pretty specific range, but the reason why is because we took a sample and we found the average of that sample. It should be very close to the average. Of the sample of 50 drivers ages 15 to 19, about 92%, I must have just averaged a little, or rounded a little differently than they did, will have a mean driving time between 24.7 and 25.5 minutes. This implies that assuming a mean of 25 is correct, about 8% of sample averages will lie outside of that given interval. Be aware, because of technology, we actually don't need to convert to z-scores first. Once we have the standard deviation of the sample means, which we had right here. Whoa. once we had right here, we could have actually just ran the calculation from the get-go. So I could do normal CDF, left bound 24.7, right bound 25.5, average of 25, standard deviation of 0.21. That's where the difference between my answer and their answer came from, was I did 3 decimal places. And they're getting a probability of 0.915, so 91.5, 92%. And that's an example of using the central limit theorem, calculating probabilities for samples. That's what's going to be very useful going forward, because that's how we conduct studies. We want to find the average value of a sample in a study. Last one, then I'll have you try one. A consumer protection agent is investigating a claim that a local mechanic is overcharging for a specific repair that has a national average cost of $190 with a standard deviation of $48. Assume a normal distribution. What is the probability a single customer at the shop pays more than $250 for the repair? So the first thing you need to be aware of is, because it's a single customer, we are not doing a sample. The central limit theorem does not apply. The central limit theorem is for sample averages. This is a single customer. So we would just do normal CDF. What's the probability? Looks like this. For a single customer, well, the average is 190. We want to be more than 250. So up here, it'll look like that. Left bound is 250 all the way up to pick a very large number as I go to the right. Average is 190, standard deviation is 48, and the probability a single customer will pay that or more is 10.6%. However, what if the investigation did a sample of 10 customers? And we want to know the probability that the sample average for those 10 customers is more than 250. Well, now we are going to be using the central limit theorem, because we're talking about a sample, and we want to find the average of a sample and then the probability associated with that sample. The average for the sample should still be the same as the population, but the standard deviation will be a lot smaller. I'll take the individual standard deviation for the population, 48, divided by the square root of 10, and now I get a standard deviation of 15.18. I can now run a normal CDF calculation again, 250 or more, so 250 all the way up to a very large number, left bound, right bound. Average for the sample should still be 190, but the standard deviation for the sample is much, much smaller if you compare it to the standard deviation for an individual. Because we're doing a sample, it should be far closer to the true average, 15.18. If I run this, I find it is highly unlikely that a sample of 10 would have a cost repair that is more than 250. So if I actually found that that shop had this occurring, that I took a sample of 10 customers and they had an average cost more than $250, what we really know then is it's highly unlikely that they're actually charging what really they should be charging. So if I compare the probabilities in parts A and B to determine if anything is unusual, well, there's an 11% chance that an individual paid more than $250 for the repair. Since that's more than 5%, it's not unusual. So the individual case, not unusual. However, there is only a 0.004% chance that the mean of the sample of 10 will pay more than $250. That is a highly unusual event. So we kind of might believe there might be something going on. Going to give you a chance to try. The average credit card debt carried by an undergraduate is normally distributed with a mean of 3,173 and a standard deviation of 1,120. What's the probability that an individual randomly selected undergraduate with a credit card has a balance less than $2,700? What's the probability you randomly select 25 undergraduates with credit cards and their the sample average for that group is less than $2,700? Take the time, give it a go, come back when you think you have some answers you want to check. This is what you should have had. The first one, you should have found there's a 34% chance that an individual undergraduate will have a balance less than $2,700. Part B, there's only a 2% chance that the mean of the sample will have a balance less than $2,700. That tends to be unusual because it's less than 5%. So we'd say it's possible that the sample is unusual, or maybe it's possible that the corporations claim that the average of 3,173 is actually incorrect. We don't know. We just know one of those things must be off. That is it for today. That's how the central limit theorem works. Thank you very much and have a good day.